Thanks again for all of you for coming. First things first, announcements. This talk will be on YouTube. It is on YouTube right now, but it will also be the recording on the Osna CPP channel probably after the next weekend. And I also said it before, this whole talk will be about an example, kind of hello world of coroutine, which you can find here. This link is also in the chat, and this link is also in the upper right corner of all the slides. If you have a second monitor, I would like to encourage you to have it open so you can have a look at it and play with it. All code examples in the slides will have line numbers which are consistent with the line numbers in this example. Let's have a short look at it together. Here in Godbold, let's go through it from the bottom to the top. You have here the main function. The main function initializes a lifetime inspector, which is a little debugging helper. It starts a coroutine named count to 10. Very simple coroutine that is stored in the local variable myCoro. Has the type hello coroutine. And here in line 62 we will resume it, and in line 65 we will destroy it. The coroutine itself you can see here in line 46 to 54. Again, a lifetime inspector is here created to see how long this coroutine lives and how long the local variables inside of that live. And it just consists of a loop counting from 0 to 9, and if I equals 5, it co-awaits std suspend always. That is, the coroutine suspends itself in the middle of the loop. You have here the lifetime inspector, as said before, just a small debugging helper which says start in its constructor and end in its destructor. Just helps when playing with the code. And then finally here line 13 to line 32 is everything you need, just like the minimal set, to have a coroutine. We will go through all of that in detail today so that you can understand this code example line by line completely. I would like to focus really on the machinery of C++ 20 coroutines today. I'd like to show you all the technical details. So really, what is C++ 20 giving us to formulate coroutines? But that also means we can't discuss other things. We will not discuss how to design a program based on coroutines, program design. We will also not discuss coroutine-based libraries, which at the end you usually will be using when using coroutines, because you really need library support usually. This talk has 4 parts. The first part is about the coroutine, what it is doing, and then we will discuss 3 important concepts. First, the concept of the coroutine promise, which is quite different from other types of promise objects that you might know. Then the awaitable, and finally the coroutine handle. So this will be the structure of the talk today. So let's get started. The coroutine. First, what is a coroutine? I'd like to try a working definition here. I'd like to say a coroutine is a function which can suspend itself. So a function which doesn't need to run to its end before suspending. When you think about that definition, what follows from it? First, a coroutine does not introduce parallelism. I think that's important to understand. There's no need for locking just because you use a coroutine, just like there is no locking just because you call a function. Then there will be objects representing suspended functions around. So when a function is then suspended, we need something to represent it, to talk to it. And at some point, the coroutines can run to an end, and then we will have these representation objects, and they will represent finished functions. Very important here in this context is to note they can only interrupt themselves. They can't be interrupted at any point from outside. So it's not like in multi-threaded programming where you have to be like afraid at any time to be interrupted by someone else. No, the coroutine specifies suspension points. It can only suspend itself and only at these predefined suspension points. These suspension points look like here our line 50 in the example. Co-await std suspend always. In general, it is co-await and then some expression. Std suspend always is in the standard library an awaitable which always suspends, as the name suggests. And this expression here after co-await, this is the awaitable that we will be discussing later. Besides that, there is also co-yield for yielding a value out of the coroutine, and co-return. And it is these three keywords that we got: co-await, co-yield, co-return. As soon as you use one of those three keywords in a function, it is a coroutine, and you must not use return in a coroutine. Besides using one of those keywords, you also need a special return type. So here in our example, it is hello coroutine. And the job of this return type is mainly specifying the promise type that you have, which will be discussed in the next section. So usually in the scope of the return type, the compiler looks for promise type as the type of the promise which is associated with that coroutine. To be precise, it's not just promise type. To be precise, there is an std coroutine traits parameterized with a return type and all argument types of the coroutine. But usually you just have a return type and inside of that return type a promise type. So that's how you define a coroutine. Use co-await or co-yield or co-return or multiple of them, and have a return type which specifies a promise type. You see that here in our example. So hello coroutine is that special return type. Co-await in line 50 will suspend the coroutine. Co-return 42 at the end will return. The lifetime inspector just helps us in seeing how long objects live. It just says start in its constructor, it says end in the destructor, so we can see whether or not objects are destroyed and when they are destroyed. Just a few words about co-yield and co-return. A co-yield of some expression is just transformed to co-await promise dot yield value expression. So the result of the expression is given to the promise, and then the promise has to create an awaitable which is then co-awaited. So once you understood co-await, you also understood co-yield. And then co-return of some expression is transformed to promise.return value expression, and then something equivalent to go to end. So co-return expression ends the coroutine and gives the result of the expression to the promise object. Yeah, but what is it? Promise object? Next section of the talk. Each coroutine has a promise object, and the compiler goes ahead and changes the code when he sees there is a coroutine, at the very beginning of the coroutine, a promise object is created for us with the promise type specified in the return type of the coroutine. Now, what is this promise? You might know the STD promise. The STD promise is a means to return a result of an asynchronous operation to the caller in combination with an STD future on the other side, and it has amongst others those interface functions, so set value to specify the return value, and set exception to notify the caller of some exception. Now the coroutine promise has similar functions. In our example, you can see that in line 24 and 25, there's a return value, int value. There's a promise accepts the co-returned value, and there is an unhandled exception function. It's not us who calls unhandled exceptions function. That is done by the compiler. So the compiler goes ahead and further changes the function and creates some try-catch block around everything. And if any exception is thrown out of the coroutine body, it will call unhandled exception on our promise object for us. But the coroutine promise has a lot more responsibilities. So what we have seen here is return void, return value, or yield value for yielding something, and unhandled exception. But the coroutine promise does much more. Maybe it should have been called the coroutine control everything object, because it also cares about suspension at the beginning of the coroutine, suspension at the end of the coroutine, creation of the return object. So the return object, not the one which is co-returned, but the return type of the coroutine. Something has to be returned before the coroutine ends. So this has to come from somewhere, and it is the coroutine promise object which is responsible for creating this return object. And then there are advanced topics. The coroutine promise object can take control over allocation and deallocation of the stack frame. It can take control over handling of errors in stack frame allocation. And finally, the promise object can even take global control over all suspension points of a coroutine. The last three are advanced topics I would not like to discuss today, but the first three you always have in some coroutine promise. Let's talk about the suspension at the beginning and at the end first. So the compiler goes on changing our coroutine. It creates a co-await promise.initial suspend at the beginning, and a co-await promise.final suspend at the end. So by implementing initial suspend and final suspend in our promise object, we can control whether or not and how the coroutine suspends at the very beginning and at the end. Let's go through it again here. So our hello promise is the promise type. We see here get return object. This is a member function which is called to generate the return object, which is returned from the coroutine at the beginning. Then initial suspend and final suspend, here returning in our example std suspend never and std suspend always. They just have to return some awaitable. And then the last two functions is what you know from the std promise, return value for handling the return value from co-return, and unhandled exception if some exception propagates out of the coroutine body. That's all about the promise. Are there any questions at this point?
So I see no questions in the YouTube chat. But also feel free to ask questions there or to ask questions here if you want. You can now unmute yourself for questioning.
So I don't see any questions, then I go on. So next is the awaitable. The awaitable is in our example here after co-await. It's always co-await of some awaitable. And take-home message is the promise controls global coroutine behavior, everything which is concerned with a full coroutine. An awaitable controls everything at one suspension point. So that's the concept. How does it do it? Let's have a look at the source code of the trivial awaitables in the standard library. So this is a source code. It is copied from the standard. Suspend never and suspend always. They have 3 functions. And we already see here for await suspend and await resume an empty implementation is valid. And we have await ready, which has to return a bool. What they do is best understood by looking at a code example. Now this time strongly simplified, so this co-await std suspend always is transformed to something like this, as I said, simplified. First, this expression here in blue is evaluated and stored in a local variable, the awaiter. And then the awaiter is asked, are you ready? Awaiter, await ready. If it says, well, I'm ready, then the coroutine is not suspended. It just goes on, calls awaiter, await resume, and the result of await resume will be what the co-await expression evaluates to. So like the return of the co-await expression. Now if await ready says false, so we are not ready, then awaiter await suspend is called. It is given a coroutine handle object representing the currently running coroutine, and afterwards the coroutine is suspended, control goes back to the caller. This is the interface, so 3 functions, await ready is simple, just returns a bool whether to suspend or not. Await resume can return whatever you like, it will be the result of the co-await expression. And then await suspend. I only showed the very simple version where await suspend returns avoid to always suspend. There are 2 other variants. It can also return a bool. Then it can change its mind last minute. So if it returns false, the coroutine is not suspended but continues. So you call await ready, it says, no, I'm not ready, I should suspend. Then you call await suspend. It says, well, no, I changed my mind, I'm ready, and then the coroutine goes on. And then there is a third option, await suspend can also return a coroutine handle, and in that case, control is not returned to the caller, but instead this other coroutine, which is represented by the coroutine handle, will be resumed. Let's talk a little bit about why we have that coroutine handle as an argument in the await suspend function. Usually you will be awaiting some operation which takes some time, like co-await a network operation, or you co-await a file I/O or something like that. But that means the coroutine will be suspended and someone later on has to resume the coroutine. And it will be that code that we are waiting on which is responsible for resuming the coroutine. So for example, your co-await network operation. That means your networking code, the networking stack, this is responsible for resuming your coroutine, and it is given here the coroutine handle, so it can do that. And then finally, co-await expression, the full story. I said co-await expression, there's the expression has to evaluate to an awaitable. That was a very short version. The full story is that expression is evaluated. And then if your promise object has a function await transform, it is given to that await transform function. That is what I meant when I said the promise can take full control over all suspension points in the coroutine. And then the compiler looks whether the object he got has a co-await operator. If it exists, it is called. And then finally in the global namespace, the compiler looks for a co-await operator which he can apply to that awaitable. And only after that the awaiter is used. QA, that's all about the awaitable. Questions about the awaitable? So I don't know whether I understood the question correctly. It is about who gets control when the coroutine suspends. And it is always the caller. So resuming a coroutine is just like a function call, but instead of executing the full function, you execute the coroutine from one suspension point where it is currently suspended at till the next suspension point. So if you have a single threaded program, you go into the coroutine and the coroutine might then co-await a network operation. Then the control returns to the caller, and then of course the network stack can't do anything because control is at the code who initialized the coroutine. That means only later when you then call maybe something like event loop.execute or something, then control goes to the network stack, and then when the network stack considers the operation done, then the network stack can call the resume of the coroutine. And then if you put a breakpoint in your coroutine there, then you would see the networking code in your call stack. Let's go quickly back. So the question was how to handle control to another coroutine. There are multiple ways. So any code can resume a coroutine, including a coroutine. So when executing a coroutine, nothing stops you from writing another coroutine.resume. But then there's also this option here. So from the await suspend function, you can return a coroutine handle, and then instead of returning control back to the caller, this other coroutine will be resumed. Does this answer your? So await suspend is called by the system, by the coroutine machinery of C++20, and the argument here to await suspend is always the coroutine handle of the currently running, about to be suspended coroutine. And then what you do with that coroutine handle there inside, that's up to the implementer. So for example, a networking library which is compatible with coroutines that has to offer networking operations which return an awaitable. So for example, you have socket.read, and then the socket.read to be compatible with coroutines has to return an awaitable, and this awaitable offers an await suspend function which is then called, and there inside this coroutine handle will be stored somewhere in the networking code, so that the networking code later can resume the coroutine once the operation is done. It's a good question. It's templated on the promise. I will be speaking about that in the last part of the talk. Yeah, there's one question. Hi, one question. Can some coroutine be executed in multiple thread objects? Yes, it can be executed in multiple thread objects, but not at the same time. So you can resume a coroutine in one thread, and then runs from one suspension point to the next suspension point, and then you can move or copy the coroutine handle to another thread. Another thread can resume it and run from that suspension point to the next suspension point. So this is possible. If you resume it from multiple threads at the same time, you get undefined behavior. Yeah, I would say if there are more questions, we discuss it at the end. And so the question was about the coroutine handle. Can it be copied and or can it be moved? Answer to that will be in the last section about the coroutine handles, and it is a coroutine handle. You have to think of that like just a pointer to the stack frame. So you can create multiple copies of that, but the state is in the stack frame, which is pointed to, and so it doesn't matter from which copy of the coroutine handles you resume the coroutine. The coroutine will run from the current suspension point to the next suspension point, and then wait there. So let's go on. And this is the next question, the coroutine handle. So the coroutine handle is a non-owning object to represent a suspended coroutine. It has the two interface functions. It has some more, but the important two interface functions are resume and destroy. So resume is like a function call into the coroutine. The coroutine will run till the next suspension point. And destroy will destroy the stack frame. And if you destroy a coroutine, also all local variables which were alive at the current suspension point will be destroyed. It's kind of equivalent to have the promise object or a coroutine handle, or even having a raw pointer representing the coroutine. So if you have a coroutine handle, you can on that handle call .address and you get a void star raw pointer. This is intended for interoperability with C interfaces. And you can call .promise, and then you get the promise object associated with that coroutine. And you can also go back. So if you have a promise object, you can call std coroutine handle from promise to get the coroutine handle. And if you have a raw pointer representing a coroutine, you can call std coroutine handle from address to get the coroutine handle. You can always create a coroutine handle of void. A coroutine handle of void can represent any coroutine, but then you don't have the left part of this graph here. So with a coroutine handle void, you can only go to the raw pointer and back. And if you have std coroutine handle of the correct promise type, you can also go to the promise object and back. More questions here? Yes, very good question. So when is the coroutine stack created and filled? So here in our example in line 59, there is count to 10. And this call to count to 10, then this will first create the stack frame. Then it will move all arguments it got into the stack frame. And then the coroutine is called and the promise object will be created then inside of the coroutine. Yes, let's go over that again. So here we had the coroutine, we had the promise, the everything controller, the awaitable controlling everything at one suspension point, and the coroutine handle, a non-owning object to represent a suspended coroutine. We had the promise with many responsibilities going through the code. So our promise is a defined here. And then here we have the getReturn object function, which will create that hello coroutine object at the beginning of the coroutine execution. And as I said, it's equivalent of having the promise or a coroutine handle or a void star. So as we are the promise, we have the promise object, and here from this promise we can create a coroutine handle representing the just starting coroutine, and then this is put into this constructor here of hello coroutine, which stores this coroutine handle in the handle member for future use. We have here the initial suspend, final suspend functions, where the promise controls suspension at the beginning and suspension at the end. We have the return value function, where the promise will be accepting the return value of coreturn, and the unhandled exception function, where the promise will be handling unhandled exceptions. We had the awaiter interface with its three functions: await ready, await resume, and await suspend. We cannot go see that directly in the code. So here the initial suspend and final suspend return awaiters. This is now the standard awaiters, but could be any other awaiter. And in our coroutine, we have co-await std suspend always. So also here we have one of those awaiters with the three functions. Yeah, and then the coroutine handle, which is here created from the promise object, stored in this handle member. And this is what we later use here in our main function. We have here our hello coroutine object, mycoro, and this mycoro has a public member handle, which we use to resume the coroutine. And here at the end, we destroy the coroutine frame. Finally, I'd like to recommend you some resources for further reading, further YouTube watching. So I very much enjoyed 4 articles by Louis Baker. Louis Baker has a small blog with 4 articles written in 2017, so it's already 3 years old. But when you print them, it's articles between 7 and 20 pages printed, and you get a very good overview over these concepts we discussed here shortly. Then I'd like to recommend to you a talk by Goran Nishanov. So Goran Nishanov is working at Microsoft for more than 20 years, and he was, I would say, the driving force behind coroutine standardization. There are lots of talks about coroutines from him, from all the CPP cons from the last years. But especially I enjoyed this one here, C++ coroutines under the covers, where he describes how C++ coroutines are implemented in Clang. He details that it is not implemented in the front end of the compiler, but in the optimization stages, and how the compiler generates from one coroutine definition multiple functions. So one ramp up function which creates the coroutine frames, handles about the arguments, and then another function doing the execution from one suspension point to the next, and he details how a state machine is built by the compiler to generate this behavior. And then finally, the standard, while the standard is extremely long, the coroutine things are new and well located at a few points. And the section 9.5.4 about coroutine definitions is, well, of course it is technical, but I would say quite readable. It's maybe 4 pages if printed, and I would say that's worth reading. Now, if you want to play with coroutines today, you have that example on Godbolt, and if you want to try it, I have some simple exercises which I would like to suggest or to propose. So here I told you at the very beginning getReturn object is called on the promise and initial suspend is called on the promise, but I didn't tell you which one is called first, so I'd like to invite you to find out. Then in the example, we only use trivial awaitables from the standard library. If you like, you could go ahead and try to write an awaitable yourself. You can just copy-paste the code from the standard library, which was also on the slides, and start modifying it, and you might try, as a very simple first step, to implement an awaitable which suspends the coroutine only every second time it is awaited. Then if you want to get it running on your machine, you might try to set a breakpoint in the coroutine, in a resumed coroutine, and then have a look, what do you see in the stack trace? What do you see in the debugger? And if there are experts around here, expert level task, there is currently a proposal under consideration of the standards committee how to implement a recursive generator in C++. This paper here, the PDF linked, is also quite readable, and it links also to some Godbolt code for the recursive generator. That's maybe 250 lines of code. So if you like, have a look there. And with that, I'm at the end of the presentation. I would like to thank you a lot for coming, for your interest. Thanks also for all the questions.